Welcome everyone to the Fields Institute. This is a lecture. This is the CRM-Fields-PIMS prize lecture, which is actually, I should say, 1/3 of the CRM-Fields-PIMS prize lecture, because if you win this distinction, which I think is thought of as the mathematics award to mathematicians in Canada. It's not always easy life. You have to travel from coast to coast. You have talks everywhere. The good part about it is you would think that the intersection of your audience is not sure about talks. This year we have Bruce Reed of Yale University. And I get to say a few of Bruce's accolades. He seems to be a real Canadian. He's gone to McGill for a PhD. I'm not sure where he did undergraduate. Also McGill. And now he's a professor at McGill. But fortunately, we got the guy from Toronto for a few minutes. That day is in the computer science department. And I believe was in Common Core. And the title of this talk is How I Learned to Do Mathematics. So, Bruce, take a brother.
Well, although this is a third of the prize talk, I hasten to assure you it's a third. I have it already, and I reworked it. So I was fortunate as a undergraduate and then a graduate student at McGill to have Vashik Vatal as a teacher and then a supervisor for my PhD. I put a picture of him up here to highlight how much he taught me about doing mathematics.
What you should get from this slide?
The other thing you should get from this slide
Is that you didn't think you had it right.
like nobody taught me how to write. You didn't handwrite? So, what I want to do is tell you a little bit about what I learned from Vashik and how I applied it. Before I do that, I'll tell you just a little bit about the field of mathematics that I work in. So, I work on graph theory. The first problem, often stated as the first problem in graph theory, is the problem of the bridges in Königsberg, studied by Euler in 1736. Was about this 4 land masses and 7 bridges in Königsberg. The question was, could you traverse each of the bridges exactly once and get back to where you started without getting wet? And he essentially formulated in what we call a graph. So he had a node for each, or a vertex for each landmass, and he had a link between each 2 landmasses for the ridges, which are called edges. This is really a multi-graph because some of the bridges have 2 edges between them instead of just one.
More of a graph where you only have to have one link between each pair of bridges.
So, graphs are a model of. I want to go back. Yeah, graphs are a model of connectivity.
It's a very simple
model, and hence therefore very ubiquitous. We just have a bunch of vertices, V, and a bunch of edges, each of which links 2 vertices. I've drawn 3 graphs here. One's a tree, one's a cycle, and one's a clique. We'll be talking about cycles of different lengths.
besides cycling 6, and cliques of different sizes.
Besides the clique.
Besides 5.
Clique, we have all possible
Edges.
every 2 vertices. So as I say, one important thing we study in graphs is connectivity. So a path in a graph is a sequence of vertices, consecutive elements of which are joined by an edge. And we'll say a graph is connected if every 2 vertices are joined by a path. So each of the tree and the cycle and the clique is connected. But if we look at this as one big graph, it's not connected.
It's got 3 components.
We have a technical.
So each of these graphs is connected, but if we view this as one large graph, it's got three maximally connected pieces, which are called components. One's a tree, one's a clique, and one's a cycle. Okay. And I thought she turned it on. Okay. Okay. Hello, universe. Okay. So, although all graphs are connected, some are more connected than others, not all graphs are connected, but those are connected, some are more connected than others. So, we see a tree, there's exactly one path between every two vertices. A cycle, there's exactly two paths between every two vertices. And a clique, every sequence of vertices is a path. We can also measure connectivity by saying how many vertices do you have to remove to disconnect the graph. In a tree, you only have to remove one vertex. In a cycle, you only have to remove two. And in a clique, no matter how many vertices you remove, it stays connected. So a tree is one connected, a cycle is two connected, and a clique is k connected for every k. Okay. So that's another routing problem you can study. Instead of traversing the edges of a graph, you can talk about traversing the cycles exactly once. The vertices exactly once. So you want a cycle that goes through every vertex. If you put weights on the edges of a complete graph and you ask for the shortest such cycle, that's the the traveling salesman problem. Here, instead of the land masses of one city in Germany, we have the shortest cycle through all of the cities in Germany, found by Bill Cook. And this picture is from Bill Cook's book, which you could read if you wanted to read more about the traveling salesman problem. And also if you wanted to see all the kind of problems that you didn't think were routing problems in graphs, but can be formulated as a traveling salesman problem, including, for example, sequencing the human genome. So part of the problem with that is solving a traveling salesman problem. But, so there are all sorts of problems that can be formulated as routing problems in graphs, but there's also all sorts of other problems that can be formulated using graphs which don't concern routing. And there's sort of another way of thinking about graphs, instead of thinking about the edges being connections which we can use to move through, is to think about them representing conflict, okay, which we want to avoid. So, for example, suppose we had courses in a university and we wanted to schedule them. So certain courses can't be scheduled at the same time because they're being taught by the same person or because there's a lot of students taking them. So you might have a vertex for each course, and then you would join two if they can't be taught at the same time, and then you'd be looking to schedule at any given time what's called a stable set, a set of vertices, no two of which are joined by an edge. And how many time slots would you need? That's the chromatic number of G. It's the minimum number of stable sets in a partition of the vertices, or in other words, a minimum number of colors you need to color so that no edge is monochromatic. Okay. So lots of other problems can be formulated as graph coloring problems. Those are the two kinds of problems that I tended to study. And important point about them is that usually we're trying to solve them on large graphs. Euler wrote in 1736 in Latin, as far as the problem of the 7 bridges of Königsberg is concerned, it can be solved by making an exhaustive list of all possible routes and then determining whether or not any route satisfies the conditions of the problem. Because of the number of possibilities, this method of solution would be difficult and laborious, and in other problems with more bridges, it would be impossible. Okay. So computational complexity in 1736 in Latin. We have a framework for that now, right? We problems in P have algorithms where the number of steps needed to solve the problem grows reasonably slowly, polynomially, in terms of the size of the input. Problems which are NP complete
are the interesting problems for which we don't expect there to be such an algorithm. The first problem to be shown in NP complete by Stephen Cook was satisfiability. And from that problem now, of course, hundreds if not thousands of problems have been shown to be NP complete. And this dichotomy is what interests us in an algorithmic sense if we're asking how do we handle large graphs. Can we develop polynomial time algorithms or not? So that's, I guess, graph coloring and rooting in large graphs. That's a lot of what I do. And how do I approach it? I want to tell you about a few approaches. One approach is polyhedral combinatorics. So I'll give you an example. I'm going to formulate coloring as an integer linear program. So that means I'm minimizing a linear function of some variables subject to some linear inequalities and to an integrality constraint. The variables have to be integer. Right? So we have here, for each stable set of the graph, we have a 0, 1 variable, which is 1 if the stable set is a color class, and 0 if it's not. We want to minimize the number of colors we use, so that's minimizing the sum of those 0, 1 variables. And what do we require? We require that every vertex is a one stable set. So if we sum up for every vertex over all the stable sets it's in, we better get a 1. And then again, I mentioned the integrality constraint. And the standard approach in polyhedral combinatorics is to drop the integrality constraint, so to get a linear program, right? And then, because linear programs can be solved in polynomial time, RMP, one then hopes to use a solution to this fractional relaxation to solve the, in general, NP-complete integer linear program, at least for some special classes of graphs, or to get an approximate solution. Okay? And just so we're clear on the difference between chromatic number and fractional chromatic number, if I take C5, I can't two-color it because I get stuck. But there are 5 stable sets of size 2. And if I give each of them weight 1/2, and all the stable sets of size 0 or 1 weight 0, that means that every vertex is in weight 1, so that's a fractional coloring using 5 halves. Okay, so the fractional chromatic number of C5 is 2.5. Okay. So one approach to solving, as I say, these large problems is polyhedral combinatorics. Another approach, what Bill Cook might call airy-fairy graph theory, is to use structural decomposition or the probabilistic method. And I think it may be clear why structurally decomposing a graph into smaller pieces is going to a local analysis. One thing I want to say today is why we can think about the probabilistic method or certain probabilistic approaches as being looking at a local analysis to get a global result. So that's then what I do a lot, not all, but a lot of what I do is use polyhedral combinatorics, structural decomposition, and the probabilistic method to solve rooting and coloring problems on large graphs, theoretically. Okay, and so as I said, I want to tell you what I learned about doing that from Vashik and how I applied it. Okay. So, whoops, no I don't. I want to tell you a little bit more about global results by local analysis. If you're going to take this approach, probably you want to look at problems where you can actually get a solution looking at local analysis. So you want to look at global parameters which are determined or approximately determined by by local parameters. So let me talk about 2 local bounds on coloring. If I have a clique, I have to give every vertex in the clique a different color because every 2 of them are joined by an edge. So that size of the largest clique is going to be a bound, lower bound on the chromatic number. Now, by the neighborhood of a vertex, I'm going to mean the vertices that are joined to it by an edge. the degree of a vertex is the size of this neighborhood. Delta is the maximum degree of a vertex, and then as many of you will know, chromatic number is upper bounded by the maximum degree plus 1, because we can just greedily color. Just order the vertices and come and color a vertex when we get to it. It's only got delta neighbors. If there's delta plus 1 colors, there'll be a color available to color it. Okay? So we have these two locally determined bounds on chi. Often they're very bad. And one conjecture I've made is that actually the roundup of halfway in between is also an upper bound on chi. Okay, so now I do want to tell you about what Vashik taught me about attacking these problems and how I applied it. So the first thing, this is look for what Hilbert calls the numerous and surprising analogies in that apparently prearranged harmony which the mathematician so often perceives. So it shouldn't be surprising that a graph theorist tells you that mathematics is about looking for links between objects. All right? In this case, mathematical ideas, mathematical proofs. The next thing may be surprising because it contradicts something I said earlier. When I said Vashik didn't teach me anything about how to write, I lied. He taught me that you write and then rewrite and rewrite and rewrite and rewrite until you get it right. Okay? And he taught me more by example than anything else. And the example is this book, Linear Programming, which won the Lanchester Prize for Exposition. And the crumpled up piece of paper on the front is exactly that, a crumpled up piece of paper indicating how often he rewrote stuff and threw it away before he was done. And certainly he taught me that it's not just about writing and rewriting your own stuff, it's about writing and rewriting other people's work until you understand it well enough that you really can make the links, understand what's going on, and then move forward. So let me give you an example of that from when I was a graduate student. We were looking on perfect graphs. There was a group of, 4 of us really, Chin Wang, Ryan Hayward, Stefano Lario, and myself that were all working together with Vashik on perfect graphs at the same time. Let me tell you what a perfect graph is. First, I need the notion of an induced subgraph. So for an induced subgraph, you take some set of vertices like the ones in these red ellipse, and you take all the edges between those vertices. This is supposed to, by the way, represent the Leaning House of Pisa. And the house you see is an induced subgraph, but that cycle of length 5 in blue, that's not an induced subgraph because we're missing the floor of the attic. Okay. And the graph is perfect if each of its induced subgraphs satisfies chi is equal to omega. Right? And this is about a global parameter coming from a local analysis, right? A clique of size C is the smallest possible thing that could tell you you need C colors, right? You can't say you need C colors if you have fewer than C vertices. So if you just said satisfies chi of H equals to omega of H, then you would be talking about global from local. Why do you add in this induced thing? There's sort of 2 reasons. If you think about it structurally, given any graph H, I can add a clique over here, take the disjoint union with a clique on chi of H vertices, and now I have a graph that satisfies that property, but it's not going to have anything nice structurally because I started with any graph H. And the other reason, as I'm going to show you now, and this is really what motivated interest in perfect graphs, is that if you have this stronger property that it holds for all induced subgraphs, then you can solve the ILP using the LP. Okay? And how do you do that? So the first thing to note is the fractional chromatic number of a perfect graph is also the clique number. Okay? The fractional chromatic number can't be any less than the clique number for any graph. Right? Because if we fractionally color the graph, we also fractionally color the clique. And the only thing you can do with the clique is to take one vertex at a time So if you're going to get them all, you need to use omega of G colors. And it can't be any bigger because the fractional chromatic number is less than the chromatic number. Okay. So we know that it's omega of G, and we know something more than that. We know that every color class of an optimal fractional coloring meets every clique of G. Because if there were a color class that didn't meet a clique, we still need omega colors here, and now we've got some more colors, the one that didn't meet the clique. Okay? So here's how we integrally cover, given that we can fractionally color, take an optimal fractional coloring, rip out any color class. Okay? The clique number goes down by 1 because this color class met every maximum clique. So that should say every maximum clique. Oh, this is so much fun. I've never done this before. It's true I can't write. Okay, sorry. So that's why this class is interesting, because you can solve the ILP using the LP. Okay, now that doesn't mean that you can do it in polynomial time, because if you think about it, the fractional coloring LP is maybe exponentially large in the size of the input graph. Okay, we have a variable for every stable set, and that may be a lot of variables. So just because we put in the graph, and in fact, the fractional chromatic number is NP complete to determine. But it turns out that for perfect graphs, you can compute the fractional chromatic number in polynomial time, and I'll explain why. Okay, and we need to look at the stable set polytope. Okay. So what's a stable set polytope? The characteristic vector of a stable set, we're just going to be in we're in R to the V, right? So we're indexed by the vertices, and XV is 1 if V is in the stable set, and XV is 0 if V is not in the stable set. And we're taking the convex hull of those vectors, or in other words, we're taking vectors which can be expressed as convex combinations of incidence vectors of stable sets, of these incidence vectors, right? And there's a relationship between the stable set polytope and fractional coloring, right? A graph has a fractional beta coloring precisely if the vector, which is always 1 over beta, is in the stable set polytope, right? This is just a renormalization, right? If it's in the stable set polytope, we have weights that sum to 1, and they sum up to 1 over beta on each vertex. If we multiply that by beta, then they sum up to beta, and they sum up to 1 on each vertex, and that's a fractional coloring. Okay? So if we can understand the stable set polytope, then we can do fractional coloring. And Vashik proved we can understand the stable set polytope, and then Grocholovas and Shriver using the ellipsoid method, and this is really one of the first uses of the ellipsoid method in combinatorial optimization, proved that that means that we can get fractional colorings in polynomial time, which then, as I showed you, means we can color in polynomial time. So this had all happened before I got to grad school. Started grad school in about 83. So that problem was solved, and the problem that remained to be resolved about perfect graphs was which graphs are perfect. Here's a graph where we know we can color quickly. We can solve this optimization problem efficiently, but what graphs are they? Okay. And Claude Berge, who defined the class of perfect graphs, had made a conjecture about that. So two graphs that aren't perfect are this one, right? Because omega of C5 is 2, but its chromatic number is going to be 3. Okay, can't two-color it. And in fact, any cycle of length 5, odd cycle of length 5 or greater, is not going to be perfect. And neither are their complements. So G complement is a graph where the same vertex set is G, and the complementary edge set. Okay? And it turns out, I won't prove it, I don't think. You can do it if you want. That the complement of an odd cycle also does not have chi equal to omega. Chi is k plus 1 and omega is k. So these graphs aren't perfect. Call a graph bearish if it doesn't contain either of these two graphs as an induced subgraph. So we know that all perfect graphs are bears, and Bears conjectured that in fact this was an equivalence. Every Bears graph is also perfect. Okay, and that was the problem that our group was working on when I was a graduate student. Okay. So, and what progress had already been made on that? One big piece of progress was to show that a graph is perfect precisely if its complement is. That this was a self-complementary class, okay, which a strong graph conjecture would imply. That was proven by Lovaas in 1972. And the proof used the fact that no minimum perfect graph contains a homogeneous set. So what's a homogeneous set? It's a set H such that the rest of the graphs either see all of H or none of H. Okay? And to avoid some trivialities, you don't want H to be all of the vertices. You don't want H to be no vertices. And you don't even want H to be one vertex, because then you have the guys that see it and the guys that don't. So you have to add in those conditions. Okay? So that was a big result. And then the rest of the results really centered around proving properties of minimal imperfect graphs, and then using those properties showing that bigger and bigger subclasses of the class of Bears graphs were classes of perfect graphs. Okay, that was what much of the work involved doing. And I'll show you an example. Clique cut sets. A cut set, well, you know what a cut set is? It just connects the graph. You know what a clique is? A clique cut set is a cut set and a clique. Right? And no minimum perfect graph has a clique cut set. And the reason for that is the following. If I have a clique cut set and it splits the graph into two parts, then if I have a k coloring of this part and a k coloring of this part, I can put them together to get a k coloring of the whole thing. Well, the only problem is they may not agree on the clique. But I can make them agree on the clique because the only way to give the clique, color a clique, is to give every vertex a different color. Right? So if I permute the color class names in one side, then they do agree on the clique. I put them together. Okay, so if I have a coloring of both sides, I can paste them together to get a coloring of the whole thing. And from that fact, it follows trivially that no minimum perfect graph has a clique cut set. Okay. And that showed, for example, the class of triangulated graphs was perfect. Okay. So G is triangulated if it contains no cycle of length greater than 4 as an induced subgraph. So every cycle has a triangular chord. Okay, or it's every chord of the cycle is a triangle, I guess. That's where the triangular comes from. Okay. And it's an old theorem of Dirac that every triangulated graph is a clique or has a clique cut set. And it follows, I mean, cliques are not minimally imperfect. They satisfy chi equals omega. They're perfect. Minimally imperfect graphs don't have clique cut sets, so it follows that every triangulated graph is perfect. All right? And this is the kind of theorem that I said that people were proving. Let me make an aside about this. This also gives you a way to color triangulated graphs, right? You find a clique cut set, you bake into two pieces. If you can color those two pieces, then we can paste the colorings together, we saw, by permuting the color class names on the clique. And if you keep breaking down, then you're going to break down to cliques, which are trivial to color, and then you can put it back together. Okay, so this is a kind of structural decomposition. Not only do we show that these graphs are perfect, we can actually get an algorithm, a polynomial time algorithm, which colors them by structurally decomposing them into small, simple pieces. Okay? Okay, but forget that aside and go back to find a property of minimum imperfect graphs, prove that a class of graphs is perfect. Class of Bears graphs is perfect. And people have done this with lots of different things. One that springs to mind is amalgam, and a class of graphs called Méniel graphs, which I'm not going to define that. And I remember there was, Vashik spent hours writing and rewriting and rewriting and re-understanding and figuring out the proof, which was not very understandable from the original paper. And he then gave us to read a beautifully written draft, which we went through and improved together again and again. And after going through all of these different classes, Vashik pulled out a common feature, okay, which is a star cut set. So a star cut set is a generalization of a clique cut set. And that's not that every vertex in the cut set sees all the other vertices, but one vertex in the cut set sees all the other vertices. The center of the star. Okay? So a star cut set is a cut set where there's some vertex which sees all the rest, in the cut set which sees all the rest of the cut set. Vashik proved that no minimum perfect graph has a star cut set. And he also proved that, if you have a clique cut set, you have a star cut set. That's obvious. If you have a homogeneous set, either the graph or its complement has a star cut set. If you have an amalgam, either the graph or its complement has a star cut set. Basically, every result which had been proven before could be proven using this. So that all of the graphs which had been shown to be perfect, almost all anyway, many of the classes, you could prove that using this result. So this seemed like a nice approach. And then Ryan Hayward, who was Vashik's student at the time, and we were all sort of looking at this problem, and Ryan solved it. So we called it weakly triangulated at the time. I've realized now a better name is strongly Beige. Okay. So a graph is strongly Beige if we've read induced subgraphs which are cycles and complements of cycles at length at least 5, odd or even. Okay. If we just said odd, that would be Beige graphs. Here we forbid the even ones as well. Okay. And the theorem was that if G is strongly Beige and it's got more than 2 vertices, then G or its complement has a star cut set. And it follows that every strongly Beige graph is perfect. Okay. And so this was a nice result. And looked at it a little bit, and what did Vashik see? One thing he saw was that this sort of G or G complement stuff is kind of ugly. You'd like to get rid of it. How could you get rid of it? And the other thing is that we dealt with evenness and oddness. Somehow we have to deal with the fact that even cycles are different from odd cycles. Okay? So after pulling out all the stuff and bringing together all the stuff that other people had done, and proving something new, then Vashik looked and said, okay, what's wrong with this? And tried to fix those two things. Okay, and the first thing is he made a generalization of star cut set, which is self-complementary, which a graph has if and only if its complement has. Okay, and that's a skew cut set. And so that's a cut set such that the complement is disconnected. We can split the cut set into 2 parts with all edges across. Okay? And a star cut set is a cut set where one of these 2 sides has 1 vertex. Right? So a star cut set is a special type of skew cut set. But the nice thing about skew cut sets, right, if AB is a skew cut set separating C from D in the graph, then CD, there's all edges in the complement, and it separates A from B in the complement. So a skew cut set, actually, Vashik called them skew partitions, because we partition into 4 sets and we get a skew cut set both in the graph and in the complement. So that seems a natural thing to do since we know already that perfect graphs are a complementary class. So the other thing to deal with was the evenness and the oddness. And this, so Vashik conjectured that no minimum perfect graph has a skew cut set. And separate even from odd, we notice something that Manuel proved around that time. So 2 vertices are called an even pair if every induced path between them has an even number of edges. Okay? So if we look at an odd cycle, then for any 2 vertices, there's 1 odd path and 1 even path. If we look at an even cycle, then for every 2 vertices, either there's 2 even paths or there's 2 odd paths. So even cycles of length at least 5 contain even pairs, and odd cycles of length at least 5 don't contain even pairs. So this seemed like a natural way to separate the odd cycles from the even cycles, and deal with the fact that strongly bearish was only about connectivity and not about parity. And then we made, and that, we sort of publicized, and there's a couple of conjectures about this in my thesis, we sort of publicized the idea that these two things together would be what would solve the strong perfect graph conjecture. And that was indeed the case in the end. The proof from early 2000s by Robertson, Seymour, Thomas, and Chudnovsky of the strong perfect graph theorem that every bearish graph is perfect did in fact use these two ideas as the main tools. And it's about I think it was about 150 pages long, the proof. I'll skip it. But what I wanted to do was to give you an idea of linking everything together, seeing what's a common theme, seeing what you need to improve on it. Right? So that was my experience as a graduate student. Let's move on to being a postdoc. I was fortunate after working with Rasha to go and work with Paul Seymour at Bell Communications Research. At that time, he and Neil Robertson were writing up what is maybe the deepest and most important result in graph theory, their Graph Miners project. Over 20 papers, over 1,000 pages. I got there and my boss, Fan Chung, explained to me that I should, and by the way, which I knew nothing about. I don't even think I knew the definition of a miner of a graph. And when I arrived, Fan Chung, who was my boss, explained to me that I should give a series of seminars on the Graph Miners project to an audience that was going to include Robertson and Seymour. I didn't really think this was a good idea. I had some project problems to solve. I didn't really want to waste my time learning this stuff, and maybe I was a little nervous. But, she was my boss, so I did it. And then, reading the stuff and reading all the other papers by other peoples and seeing the links, I wrote a manuscript which hasn't been published yet. 275 pages of it are written. So that may seem like a waste of time. It wasn't really, because I wrote scores of papers in this area. And the reason I could do that is because I got this basis, starting with Fan's idea that I do this seminar series. You can't read that, but it doesn't matter. Okay. So let me just tell you a few things. I don't have time to really give even a brief introduction to graph miners, but I want to talk about how it links to these idea of linking things together and how it links to the global analysis, getting global properties via local analysis. So very, very brief discussion. So I'm going to talk about models. So a model of a clique in a graph, a KL model is just L trees, every two of which are joined by an edge. So if you contract all of those trees down to vertices, you get a clique, and that's what links this idea of a clique model to a clique miner, which some of you may be more familiar with, but I'll talk about it in this format. Okay. And one wants to get a structure theory for graphs without clique models. One of the motivations for this is Haggerty's conjecture, which I'll tell you in a second, but one wants to try and understand what is the structure when we forbid these structures. What's the structural properties of the graphs that we get? What are the global properties that we get? So it's not hard to show that if G arises via clique identification from graphs without KL models, then it also has no KL model. I'll leave that as an exercise. And basically, there's a theorem of Wagner from 1943 that G has no K5 model precisely if it arises from clique identification graphs which are planar, i.e. can be drawn in the plane so no edges cross, or one special 8-vertex graph, cycle length 8 with all long diagonals. Okay? And this is an if and only, it's well known that planar graphs don't have K5 models, and this special 8-vertex graph doesn't either. And precise characterization. Okay. Sorry. Well, it's a precise characterization. So it's not actually arises in this way, but it's a subgraph of a graph that arises in this way. Okay? But just like, okay, and then let me just say that there's actually a similar theorem for graphs without a KL model. Okay, and that's about 1,000 pages of the graph minus structure theory, and I'm not even going to state the theorem for you. But it is the same thing as cutting down on cliques when you're trying to color a triangulated graph. You decompose using the cliques of the clique identifications. You get down to these simple graphs. Here, planar graphs or 8-vertex graphs. You solve the problem, and in this case, a problem you can solve on it. Lots of rooting problems are easy on planar graphs because you can't do that much because you don't have much topological complexity. So, just as by coloring triangulated graphs, this structure theorem gives you a way of solving lots and lots of optimization problems on graphs without KL models. So some of the work we've done in the area is with Kenichi Kawabayashi and Zentao Lee. And I have the fastest algorithm for building the structural decomposition that's guaranteed to exist here. Zentao and I, his PhD thesis was to get a linear time algorithm to determine if the graph has no K5 model and build the structural composition if it does. And as I say, scores of other papers written. And again, this is all about structural decomposition so that you can get a global result using a local analysis. Okay. All right. And then let me just mention, as I said, although it hasn't been solved yet, one of the main impetus for this work was Haberger's conjecture, which says that if G contains no KL model, then it has an L-1 coloring. So by Wagner's theorem, the case L equals 5 of this is equivalent to the 4-color theorem that every planar map has a 4 coloring. Okay. And Paul Seymour and I proved that if G has no K model, then it has a fractional 2L-2 coloring. So not L-1, we're out by a factor of 2, and not integral, but fractional. And we did this, again, we did this by finding a spanning triangulated model of any graph, okay, such that, with certain properties. That's all I'll say. But anyway, it went back to the decomposition theorem about triangulated. It went back to the perfect graph stuff, and that stuff came in here in a completely different domain. Okay, and that's the point I wanted to make about this. Stuff comes up that you wouldn't expect. The surprising harmonies. Okay, so that's the thanks, Van. You know, it wasn't that I was a far-seeing visionary. I was just told what I had to do by my boss. I'm very grateful for that. Okay, and now the third time, and this is the one I got on my T-shirt. The third instance of this approach that I want to talk about is my work in graph coloring by the probabilistic method. You know, I still regret giving in to Mike and letting him use and there instead of via, but anyway. Graph coloring in the probabilistic method. I remember when Mike suggested, we've been asked to write a survey paper on graph coloring in the probabilistic method, and Mike said, I'm pretty sure Mike suggested this in a hotel room in London. He said, you know, why don't we actually write a book? Now, he wasn't my boss, so I could have told Mike to take a hike. But by that time, I kind of decided that this was sort of a good idea. So we wrote, we didn't actually know very much when we decided to do it. And we read everybody's paper, and we tried very hard to put them in a common framework, rework them, rewrite them until they all were sort of variants of the same paradigm. Okay? We worked for that a long time. We worked on that until we were sick of each other, and then we worked on it for quite a bit more. But we seem to have gotten over that. And I want to tell you a little bit about this work, and in particular, I want to tell you why the probabilistic method, at least the tools we were using, are getting global results from a local analysis. And I also want to tell you how it links to polyhedral combinatorics. You know, because some of you might think that it's whatever that term is. Okay. Okay, so here's a simple tool, right? if there are any probabilists in the room, they'll probably leave at this point. But here's a very simple tool. So if a family of events satisfies the sum of the probabilities is less than 1, then with positive probability, none of the events occur, right? The probability of the union of events, right, is less than the sum of their probabilities with equality if and only if they're, well, with equality if they're disjoint. And so if the probability is less than 1, that means that probably none of the bad events occur. Okay? And let me show you how you use that to get an upper bound on chi using the fractional chromatic number, which is, of course, a polyhedral approach, right? Approximating chi using the LP solution. So I'm going to get a log upper bound. This result was originally proved by Lovaas in the 70s using. So the first thing to note is the probability distribution of the stable such that the probability of every vertex, the vertex is in a random stable set, is 1 over the fractional chromatic number. What's a probability distribution on the stable sets? It's a convex combination of stable sets. It's a point in the stable set polytope, right? This is the same as saying that if you can beta color, then 1 over beta, 1 over beta, 1 over beta is in the stable set polytope, which we already saw. Okay? So there's this connection between the stable set polytope and probability distributions on stable sets. The connections being they're the same thing. Okay? And so if you're going to use that fractional coloring, you're going to use that as a probability distribution and pick random stable sets from it. Okay? And if you pick enough of them, what's the probability that you don't pick a vertex? Because all you need to do is cover the vertices. If you hit a vertex more than once, you'll drop it out, and you'll get your partition. You'll get your coloring. So what's the probability you don't get a vertex in one of the stable sets? The probability you don't get it in one stable set is 1 minus 1 over chi f, and these choices are independent. And I picked the number of stable sets. This should be the number of vertices of G. Well, maybe I'll do it again. Okay. And then there's n of what v events that we're trying to avoid. Each is probably less than 1 over v. So with positive probability, by a remark from last size, we don't miss any of them, and we get a coloring. Okay. And this is getting a global result by looking locally, right? Because we looked at each vertex on its own, right? But the problem is it's only a global local thing because we still have to sum up over all the vertices. Okay, so that summing up over all the vertices is what means we get a log n there. Because we need the probability to be 1 over n. So we need a log n approximation. So if we want to get a better approximation factor, we're going to have to not sum up over everything. Okay. So how do you get like much better approximations? You need a local lemma instead of a global local lemma. And you need bells and whistles. Right. So, what's a local lemma? Well, I most spoke it's a Lovaas local lemma. Okay, and that says that instead of summing up over everything, you just have to sum up over things on which, well, mutually independent. So for every event, you have a set of events. It's mutually independent of everything else. And then as long as the sum over the things which is not mutually independent of, the probability is less than a quarter, then with probability none of the bad events occur. So what happened? We went from global to local at the cost of a factor of 4 in the bound, which is pretty good because if it's less than 1, it's usually way less than 1. Okay? And so let me just give you an example. I'm going to talk about an R-regular graph. So that says that the size of the neighborhood of V is R for all V. Every vertex has R neighbors. And I want a 2 coloring. So there does not exist a monochromatic, not edge now, but neighborhood. Okay? I'm just going to check my time. 10 more minutes. Yeah, okay, good. So I will do these then. So what are my bad events? So BV is event, E is monochromatic, or a neighborhood of V is monochromatic. Right. What's the probability of BV? It's 1 over 2 to the r minus 1. I mean, okay, and my space is, my space, I won't write it down. It's uniformly random 2 colorings. Every vertex gets red or blue with equal probability independently. Right? So the probability in the neighborhood of our vertices is all red is 1 over 2 to the r. All blue is 1 over 2 to the r. Probably it's monochromatic is 1 over 2 to the r minus 1. Look. And here's BV, here's NV, and here's NW. And if they're disjoint, then whether or not this is monochromatic is independent of whether or not that's monochromatic, because this depends on these vertices, and that depends on those vertices. So we can let here, what is S of BV is just going to be BW such that NV intersection NW does not equal the empty set. Right? And the size of S of BV is less than or equal to R squared. Because I got R vertices here. Oh, sorry. No, that's right. I've got R vertices here, and each of them is in at most each of them is in R edges. So even for all these edges, no, that's right. So that's R squared. Even if all these edges are disjoint, we get it's at most R squared. So as long, what is this sum? Then this sum, so as long as R squared over 2 to the R minus 1 is less than a quarter, then I can get my 2 coloring. So as long as the R is at least, 7, 8, whatever it is, you get a 2 coloring, right, with no monochromatic neighborhood. Okay? So you see, I hope the ideas, right? I mean, by only summing up over the things that are dependent on this instead of having a sum which is bounded by a function of n, it's bounded by a function of delta. Okay? So you just need to probably be small in terms of delta. And so you win big time. Okay? And so that's a main part of the approach. I mean, and there's lots of bells and whistles. I don't know if I'll say anything about, I guess I can say a little bit. Special probability distributions, you need to have this independence property, right? When you're picking your stable sets, you need, here I said just color every vertex separately, so certainly things that are far apart are going to be independent. But if you're picking from a fractional coloring, trying to get an integral coloring, you need that your fractional coloring has independent properties, that what's going on in one part of the graph is essentially independent of what's going on in another part of the graph. And so certain classes of graphs have such optimal fractional coloring, certain don't. Okay. Recursive coloring, think about coloring a clique. Okay. I mean, you know how to color a clique optimally pretty easily anyway. You just give every vertex a different color, but suppose you didn't realize it was a clique or it was contained in another graph. Then every time you're coloring the clique, you're either, you're picking a vertex. Okay? And if it's a clique of size C and you pick C vertices at once, right, then, some guy, you get about a proportion 1 minus 1 over E of C of the vertices would be picked, right? Some vertices get picked multiply, some vertices don't get picked at all. So what you're better off doing is picking little o of C vertices, throwing them away and going again. And that way, instead of hitting lots of guys a lot and some guys none, you spread it around and you're more likely to get an optimal coloring. So a recursive procedure works better. Graphs which are really hard to color are graphs which look like cliques. Okay, if you've got no edges in the neighborhood, that's going to be a big win for you. because you're not going to have much conflict there. So you have to deal with graphs which have neighborhoods which look like cliques, and it turns out what you do is you get a structural decomposition. You pull those graphs off, you pull those parts of the graphs off, and you get these small clique-like pieces with very little connection to the rest of the graph, and you can handle them essentially separately, but not really. Okay, but by pulling them off, you manage to do better. And I won't say anything about concentration inequalities, but this was a relatively easy proof. The proofs can get significantly more complicated and do. And I guess I could have put about 20 or 30 results on this slide, but I didn't. One result I did with Mike using this technique, which uses most of the things that I talked about, is coloring total graphs with omega plus C colors, or in other words, total coloring graphs with delta plus C colors. I won't define that. I don't really want to talk about the results because that's not the point. In fact, so that's what I'll do. I'll just say I don't want to talk about the points because that's not the point, right? Let me say what I really want to say, which is, I'll give this an alternative title, right? It's not about the results. That's not the point, right? You know, I think there's a real emphasis on we got to get the results out, and then once that's done, it's done. To my mind, it's all the stuff about learning all the other stuff, writing it until you really understand it. Learning how to do that's going to stand you in good stead in the future, right? And it's what I found worked for me. So I'll leave you with that. Thank you.
Thank you very much for your personal tale, along with many results. I'm sure there are questions. There's certainly time for questions or conjectures, counterexamples. If anyone would like to
You asked about reading and writing and rewriting. It was probably very appropriate 20 or 30 years ago. But now with the internet and things are evolving, if we were to follow your advice, then in order to get better, it's supposed to be rewriting what it is.
I certainly think that there's heavy pressures in the academic world going in the opposite direction, and I think they're wrong. I think they're badly wrong, and I think we should find out answers.
I certainly agree that those pressures are there. I certainly agree that those pressures are there. And that's a bad tendency. Maybe if you write and put on the archive and you write free. I'm not sure. That also I don't agree with, but fight fire with fire.
I guess I know this way part of I mean, can be used
It can be used to, it's useful for separation stuff, right? Like where it's more useful than in the kind of tree couples I was talking about in the tree branch addition or and it's also useful in markup chain stuff. I didn't talk about that at all.
Talk about connectivity. Okay, other questions, comments? I have not a question, but something to give to you.
Okay.
So, just want everyone to witness this, that it's a prize. And the prize comes in an envelope. Congratulations.